Hello, everyone. Welcome. My name is Jennifer Nyman. I'm with Geosyntec Consultants. We are the coordinator of the webinar series on behalf of SERDP and ESTCP. Today, we will have a brief overview of SERDP and ESTCP, followed by 3 technical presentations on DoD-funded research to predict and reduce corrosion of DoD assets. First, Captain Brock Andrews will discuss the cumulative exposure algorithm to characterize the corrosion potential of an asset based on environmental exposure. His presentation will be followed by a question and answer session. Next, Dr. Christine Sanders will present models that assess coating life based on the environment and use, followed by a Q&A session. Finally, Dr. Steve Castro will focus on modeling changes in the coating system as a result of various exposure conditions, using electrochemical impedance spectroscopy and stress fields in the coating system. After a question and answer session for Steve, we will conclude the webinar today with a Q&A session for all 3 speakers. The next few slides provide some instructions on optimizing your webinar experience. If you haven't done so, download Zoom at the link shown here and provided to you in your webinar registration confirmation email. If you cannot download Zoom, you can view the slides using a compatible browser like Firefox or Edge, and by creating a free Zoom account. If you really can't view the slides, or if your screen freezes, you can try keying Control and F5 to perform a hard refresh if it's not working. If you're accessing the audio through your computer, you can click on the arrow next to the Join Audio button and select Test Speaker and Microphone, and follow the prompts as they appear on your screen if you're having any audio difficulties. If you continue to have difficulties, please call into the conference line shown here. You can also submit a comment using the chat box for any technical difficulties, but please reserve the chat box just for those types of comments. The Q&A button should be reserved for questions for the speaker. In case of continued technical difficulties, you can download a PDF of the slides from the webinar webpage, and you can call into the conference line given to you in your email. We will also be live streaming the webinar on the SERDP and ESTCP YouTube channel at the link shown here. Today's broadcast will be listen only. You can submit questions by using the Q&A box on your screen. You don't have to wait until the Q&A period to submit your questions. And in fact, we encourage you to submit questions in advance of that session. When you do submit a question, please add your organizational name at the end of the question. With that, I would like to introduce Dr. Robin Neeson, who is the SERDP and ESTCP Program Manager for Weapons Systems and Platforms. Before joining SERDP and ESTCP, Robin worked at NAVAIR's Weapons Division China Lake in California. Robin, please go ahead.
Well, thank you, Jennifer. I'm very pleased to welcome everyone to today's SERDP and ESTCP webinar. SERDP is the Strategic Environmental Research and Development Program. It was established in 1991 by Congress as a partnership between the DoD, Department of Energy, and the EPA. SERDP's mission is to identify and address high-priority environmental science and technology opportunities which focus on DoD requirements. SERDP funds both fundamental research as well as advanced technology development that will ultimately impact real-world environmental management. ESTCP is the Environmental Security Technology Certification Program. Here, we demonstrate innovative environmental and energy technologies. These investments capitalize on past efforts under SERDP or other research programs and are designed to transition technologies out of the lab and into the field. Especially important in all ESTCP demonstrations is the transition to implementation and regulatory acceptance. SERDP and ESTCP are complementary programs with much of SERDP research occurring in the lab and pilot scale with occasional field efforts, while ESTCP demonstrations are primarily at the pilot and field scale, although occasionally supporting lab efforts are conducted. There are several environmental drivers for the type of work funded by SERDP and ESTCP, with the underlying objective of sustaining DoD ranges, facilities, and operations. This, as you can imagine, is a broad undertaking and includes maritime sustainability, management of threatened and endangered species, climate impacts, unexploded ordnance, and munitions constituents, as well as other environmental drivers. One key environmental driver is the reduction of current and future environmental liabilities. This involves addressing contamination from past practices, including impacts to groundwater, soils and sediments, UXO contamination, and developing management approaches for contaminants of emerging concern. The second part of this is pollution prevention, with a focus on eliminating likely environmental pollutants or hazardous materials in manufacturing, maintenance, and operations on our installations. We have several main focus areas for research and development at SERDP and ESTCP, as shown here. Weapon systems and platforms is the topic covered in today's webinar. As mentioned earlier, technology transfer is very important within the SERDP and ESTCP programs. Technology transfer efforts include the development of videos, training workshops, and guidance documents. The webinar series is a significant component of our technology transfer efforts. Our webinar series highlights research and demonstration efforts from all of our program areas. Upcoming webinars will cover a broad range of topics, including applying open source tools to optimize building operations and forensic techniques for differentiating PFAS sources. Registration for 2022 webinars will be available soon. You can find additional information about upcoming webinars at this link. All past webinars are archived and can be accessed using this link. And the 2021 SERDP Symposium is coming up. It'll be a virtual event running from November 30th through December 3rd. And at this symposium, we'll showcase the latest technologies that enhance DoD's mission through improved environmental and energy performance. I would encourage you all to register for the symposium. And finally, I'll just remind everyone that a copy of the presentations from today's session can be downloaded from the webinar page. We would appreciate it if you can take a moment to complete the survey that will pop up on your screen at the end of the webcast. Hope you enjoy the webinar today.
Great, thank you, Robin. It's now my pleasure to introduce our first speaker. Captain Brock Andrews is a lead aerospace corrosion engineer at the Air Force Corrosion Prevention and Control Office at Robins Air Force Base in Georgia. At his current assignment, Captain Andrews manages an extensive technical project portfolio focused on technology insertion, airworthiness, and employee health and safety. Captain Andrews earned his master's degree in engineering management from Embry-Riddle Aeronautical University. Captain Andrews, please proceed.
Okay, good afternoon, everyone. Can you hear me?
Yes, we can.
Okay, thank you very much. So thank you for the introduction. Yep, my name is Captain Brock Andrews, aerospace corrosion engineer at the Air Force Corrosion Prevention and Control Office, Robins Air Force Base, Georgia. And I'm going to give a little overview today on the status of the corrosion monitoring system to reduce environmental burden and corrosion maintenance costs. It's a little bit of a mouthful, so internally we just call it the WASH study, and you'll see why here in a minute. There we go, arrow keys. All right. So this is a little bit what I'm going to talk about today, just the outline here. So the background of the project, why is corrosion maintenance important, a little bit about what we do, why we do it, and when we do it. The project objective, so you know, the whole premise of ESTCP, right, at least what we're going under is environmental impact. So how can we improve efficiency and reduce waste through better performing some of the maintenance actions that we do, particularly the WASH. So, and then the methodology of the test, a little overview of the test articles that we're using, where we're actually doing our testing, and some of the parameters that we're using and collecting. Results, is a little bit premature. I guess we should really say results so far. This is an ongoing project, so we're still in the middle of data collection, trying to wrap up, but we keep thinking of a little bit more that we want to go out and get, or maybe we just haven't seen enough. So we'll go over that, and then again, conclusions and path forward, at least what we've seen so far and where we see this going in the future. Okay, so the background. Each year, I'm sure it's no surprise to everyone, each year thousands of U.S. Air Force aircraft and support equipment are inspected and washed as part of the overall corrosion maintenance plan. Generally, those are done in accordance with Tech Orders 11691 and 3513. That's for aviation and ground equipment, respectively. And we say thousands, we really do mean, the Air Force inventory of aircraft is somewhere around 5,000, and then the ground equipment inventory is probably many thousands more than that. So we wash because pollutants, minerals, chlorides get deposited on the aircraft. They don't stay clean. And so they do need to be washed to reduce corrosion impact due to those deposits. However, every time you wash, you're looking at bringing an aircraft down at least for several hours, and a team of maintainers to go ahead and do that wash and the pre and post actions that need to be done. So you're losing weapon system availability, particularly if you're washing when you don't have to. You're losing availability for really no good reason. So it's labor intensive, and it generates hazardous waste. A lot of the aircraft in the inventory right now are coated with chromated paints, which hexavalent chrome has been a hot topic over the last few years as causing cancer if it gets airborne and gets breathed in, or you track it on your clothes, exposure to your skin. It's not good stuff. But there are other hazardous materials on aircraft as well. And you look at cadmium plating, other various heavy metals that might be used in engines or landing gear, even things such as just fuel residues or jet exhaust and soot that gets washed off the aircraft. All of that stuff is hazardous both to personnel and to the environment. So if we can reduce the amount that we're washing, we can reduce the amount that those personnel are exposed. And down there at the bottom box there, the Air Force spent, this is slightly out of date data being from FY20, $4.3 billion on the prevention, inspection, identification, and repair of corrosion. And that's per the LMI cost of corrosion study from FY20. Some of the estimates in more recent years are actually closer to $5 billion. So we spend a lot of money on this, and we're thinking maybe we don't have to. So the project objective, it's pretty simple, and like I said before, we want to improve weapon system availability and reduce the hazardous waste generation generated by corrosion maintenance processes, particularly the wash, through the use of computer learning and predictive algorithms. We want to be able to plug data into a computer and have it say, hey, this is your optimal time to wash. No more, no less. So the methodology. This is the sort of overview of what we'll get into, and you can see, it looks like my cursor is working down here at the bottom. It's kind of the flow chart of what we're looking at. So sort of a step-by-step into what will eventually become a holistic algorithm. But the first part there, train the cumulative exposure algorithm, the CEA, to characterize corrosion potential based on environmental exposure. So there will be a little bit more on that later, but basically, how corrosive is the environment that the aircraft is exposed to, or the piece of ground equipment? Then the next step, utilize that exposure algorithm to output as an input for a Cvm Plus algorithm. And Cvm Plus is a new thing, sort of new for the Air Force, where it's not only corrosion maintenance, but basically combining every aspect of aircraft and ground equipment maintenance into a holistic model-based approach. and then optimize those maintenance actions based on the exposure conditions and everything else that's being fed into Cvm Plus, which there's a lot there. It's too much to include in a chart like this. So a little bit more detail, just on the test articles here. So I guess the first thing to mention is the sensors that we're using to collect all of our environmental data. So using the Luna LS2A and CoreRes sensors, and previously we were using the Luna Acuity LS sensors. As those reach end of life, we've started transitioning over. So you can see the just the images there, those sensors, pretty basic, collecting surface temperature, air temperature, relative humidity, and taking a conductance measurement as well. So that's the sensors. You can see down there in the bottom of the chart the various panels that we're using. So we've got lap joint panels, which are there in the middle. Those are both painted and unpainted. And you can see it's 7075 and 2024 aluminum. There's various fasteners, titanium, cadmium, cadmium steel, and the A286. And then there's not a bullet for it. You can see the witness panels. It's the same metals for the witness panels. They're painted and scribed. It's just standing out by themselves for exposure. And then on the far right is the simulated aircraft structure, the SAS boxes, which is basically a more complex version of the lap joint panel. They're again painted and fastened together with essentially a sealed interior cavity to simulate what an aircraft would be like. And to give you an idea of scale, those are about 2 feet by 3 feet. And then the down there, the blue box basically says environmental data from those sensors recorded every 30 minutes. So far, we've collected over 8 million. I think it's even closer to 9 million lines of data now from those sensors. And then the general weather data we get from just NOAA weather stations at the sites. So a little bit more about the test articles. They're all coded using legacy coding systems. I mentioned before that hexavalent chrome has become kind of a hot topic, and we're trying to transition the fleet into non-chrome paint systems. That particular part of it didn't make it into the test plan, so they're all using the chromated paint systems right now. We do see a future in which we do some testing, some similar testing for non-chrome systems, but this is just within the scope of this test here. The coded test articles, the flat panels, the lap joints, SAS boxes, and the CoreRes MSPs. The fang surfaces, you saw the lap joints in the previous slide. Those are the fang surface is primer only, and then the rest of it has the top coat on it. All the fasteners, in order to give it sort of the worst case scenario, all the fasteners are dry installed. Obviously, on an aircraft, you want to generally wet install to give a good seal, but they're dry installed, so we don't have to leave these out for 5 to 10 years. We hope, we're hopefully getting good data after a couple of years of exposure. And the uncoded test articles, the LS2A sensors have a bare electrode there for the conductance, and then the unpainted lap joint panels are actually just taped, and it's not any kind of special tape, I don't think. It's just to give it a little bit of a barrier before it starts corroding. So they're just taped, and I think there's another picture of that later on. The outdoor testing, here's where we're testing at. These were selected based on severity, and I think there's another slide showing what the severities are for each of these. But you can see Kadena, Anderson, probably two of the worst places in the Air Force for corrosion severity, followed closely by Patrick in Florida. And then we have Westover, Hurlburt, Ellsworth, Travis, Aviano, Dias, and Savannah. And that gives us a pretty good cross-section of the aircraft that are included in this test as well, which is the C-130, C-5, B-1, and H-860, giving us a pretty good representation of various different aircraft across the fleet. So the wash cycles, how are these things actually being washed? So the exposure coupons, the test stands that are deployed out to these sites, they're all washed according to the ESI that you know, the air base of wherever they are at. So you can see there on the right, the table, we have mild, moderate, and severe ESIs, and you can see the wash frequencies for those sites. The 1x frequency there is what is called out in the tech order currently. So you can see 180 days for mild, 90 days for moderate, and 30 days for severe. And then each site has a no wash, and then we do a 1.5 and a 2x at the moderate and severe as well. So the stands themselves are actually washed in accordance with TO 3513. That's the ground equipment wash instructions. And that was done because the stands are actually deployed in ground equipment ramp areas. And that's what those particular maintainers are more familiar with. And that was just to save a little bit of time and reduce the burden on the maintainer's part. So they're using the approved detergents and pads for ground equipment. So here's a little bit about the exposure algorithm. Like I said, sensor data is captured every 30 minutes for the sensors there. And this is basically being thrown into a table to compile the corrosivity matrix to train the CEA. So time, you know, just the timestamp for the data that was taken. The corrosivity, that mu there, is actually a calculated value based on the next variables: humidity, temperature, surface temperature, and conductance. And you can see just down at the bottom, it's not the exact formula, but you can see it's a function of those things. And that's basically really just a cumulative coefficient that ticks up over time that will get fed into the next algorithm, which is the Cvm Plus. So the Cvm Plus algorithm is tracking cumulative environmental exposure of the aircraft based on where they are at any given time. Generally, they're at their home station, but they take TUIs out to various places and should be washed accordingly on that. So a little bit change from what's currently in the TO. They're based on their need, not on a set calendar interval from their home station. So you can see there a slightly different table: aircraft tail number, its current location, which would also include, I mean, this would be a very large table, where it's been, the last date that it would wash, which would basically reset that coefficient to 0, and then the daily exposure index, the cumulative exposure state, which is basically the just the sum there. You can see at the bottom the sum of the daily exposure indexes, that mu from the last chart. And then it will spit out a next wash due date, or a wash window. So don't wash before this, but do wash before this date. So a little bit on the test articles, the results that we're looking at so far. These particular panels are the 6061 and 4130 coupons after 3 years at Kadena. And we would have actually expected to see a little bit more damage, but this is actually where we're at right now. So little limited difference in corrosion damage based on the different wash intervals. So the left two panels there as a 30-day interval and a no wash, and you can see the aluminum oxide there in the scribe, that white stuff. Visually, not much difference, and actually, I mean, to the naked eye on these highly compressed pictures, it looks like not washing might actually produce less of that oxide. But of course, we'll bring these panels back into the lab and actually evaluate and do mass loss and actually see how deep it went and all that stuff. And then there on the right, you can see the 30-day interval and the no interval for the steel panels. Really, again, not much difference there. In this case, it looks like washing might actually be a little bit better for the steel, especially around the edges of the no wash. You can really see a lot of bubbling and probably exfoliation there for the steel. Again, the lap joint panels after 3 years at Kadena, the 2024 top plate and the 7075 bottom plate. Again, these have the painted ones have just the primer in between. The unpainted ones are completely unpainted with just the tape barrier there. So you can see just the difference between these two panels. The painted, they're all scribed. So the painted panels, really not much corrosion visible there. Again, you can see a little bit of the oxide showing up. The unpainted lap joints on the right, all of that yellow stuff, I think is just residue and remnants from the tape. And you can see actually some reasonably significant corrosion there in the fasteners and along the bottom edge of the seam. Cast boxes, same kind of thing. 3 years at Patrick this time. And you can see a little bit of difference. Again, highly compressed pictures, hard to tell, but it looks like actually washing, based on the pictures, washing at the 30-day interval for the exterior might be worse than not washing. But I think we're showing some data where we're actually showing that the opposite might be true. And then the right pictures are just the interiors. You can see they're primer only. Hard to see the scribes there on the fasteners, but they're scribed, so so we get that cross, galvanic couple there. So here's some data that we've gotten so far, and there's a lot of data. It's really too much to show in a 20-minute presentation like this, but we've combined some stuff here so you can see the mild, moderate, and severe ESIs that we've got there on the left, and then we combined in these charts the inner mold line and the outer mold line for the SAS boxes, and these are the conductance measurements taken by those Luna sensors. And so you can just see, over time how the conductance is increasing, and the various wash intervals that happen, so the different color lines. Again, this is raw data, so we try not to draw conclusions from this. This is, pre going into the algorithm, but you can see that actually the inner mold line in all three ESIs is more severe, or at least more conductive than the outer mold line, regardless of the wash frequency. So, like I said, this project is ongoing. We've had 3 years of exposure at some sites, and we're still collecting data. The majority of the panels are still out there. We've collected some and have analyzed them, but it's ongoing. But what we've seen is that the difference between the panels is sort of minimal and less than we would have expected in terms of the different wash frequencies. And so that tends to point towards maybe washing actually isn't as important as we thought. But again, this is sort of a this is a test, and we do know that washing does help on actual aircraft. So actually getting to a point where we can correlate between the two will be important for the final results of this project. So we're continuing to collect the data and doing the analysis. There is a first draft of the algorithm that has been done, and it's being refined and trained as we speak, and hopefully is ready to go to actually start performing field service evaluations by the spring. So we're continuing the development of that algorithm and beginning the rollout of actually the module that will go into Cvm Plus. So we've started working with the Rapid Sustainment Office in the Air Force who is developing that full Cvm Plus system and talking about how our module will fit in with that. So yeah, I mean, additional information, obviously SERDP ESTCP is a great place to start. If you want to contact myself or my office about this project, go ahead and reach out to me at that email address there. That phone number is my desk phone. No one's there because we're still teleworking, but go ahead and shoot an email over to me there, and I will get back to you as soon as I can. And I think the next slide is just the Q&A. And I did see a couple of questions pop up in chat, I believe.
Yes, thank you, Captain Andrews. We do have a few questions, and to the audience, feel free to continue to type in your questions in the Q&A box. So first, have you considered using accelerated environmental testing, like with salt fog?
Yeah, so we do use salt fog chambers for other kinds of testing. However, it wasn't selected for this project just based on you would have to put the test article in the chamber, expose it to the salt fog, take it out and wash it, and then put it back in. And you know, over several, well, I mean, it's accelerated testing, so you know, maybe a year you can get the same kind of results. But a salt fog chamber is a lab type of test. You know, it's a controlled lab environment, and you know, like I said before, it's pretty well known that correlating lab results to real world is notoriously difficult, and so we wanted to at least get it, you know, the test sort of as close to the real world as possible. So we do use salt fog. It's just not getting used for this test.
Okay, thank you. And do you ever tie in climate models to try to predict for future corrosive impacts?
Okay, so that's a good question. So there's actually some parallel projects going on. This project that I just talked about was really focused on how effective is washing. Can you wash too much? How little can you get away with washing? So the parallel projects then we are actually doing climate model assessment where we're looking at, you know, collecting all kinds of data. Again, you know, temperature, rain events, humidity, various pollutant deposition, so sulfur dioxide, ozone, chlorides, and how corrosive a particular environment is. So the end goal would be to combine that with the wash study to actually start saying, okay, this aircraft has been exposed to this severity, this actual severity, and not just the table that's in 11691, and this is when you should be washing and performing your other various preventative and predictive corrosion maintenance.
Okay, thank you. There were some interesting results that you showed about wash frequency, and there were some questions about the actual aircraft wash down. Can you give us any more information about what's involved in that? And do you know if there are differences in corrosivity in the data following a single wash?
So as far as corrosivity after a single wash, generally speaking, the assumption is that at least the outer mold line is clean, and as long as the water doesn't hang around too long, the corrosivity for the outer mold line is basically reset to zero. And it's not exactly accurate, but that's sort of the control assumption. Now, if a coating has been compromised, if the coating around a fastener, for example, has been compromised, or along a seam has been compromised, and water is allowed to get inside the aircraft to a place where it's not supposed to be, then in those cases, and I think the data kind of pointed to that in the slide where I showed all those colorful lines, is that the washing is actually not great for the interior of an aircraft if the coating has been compromised. And so in those cases, oh, excuse me, we would actually expect to see the corrosivity go up.
Okay.
So I think that was the second part of the question. What was the first part of the question again?
Oh, just if you had any more information or a quick summary of what's involved in the wash. Is it just water, or is it does it involve a cleaner?
Okay, yeah. So the washes themselves, and you can look them up in detail in Tech Order 1-1-691. Those should be searchable by everyone. They're public release. But yes, for the washes, we do use specified detergents and scrubbing pads. It's not just water. We do also perform clear water rinses, which are done in particularly salty environments, and those are just water. Basically, a nozzle spraying the aircraft down with water. But the washes are done, yeah, with detergent and scrubbing materials.
Thank you. And one last question. What changes to the TO 1-1-691 wash table might be expected as a result of this project?
So I don't really want to get ahead of myself. As far as the change to the 691 in the future after this project is fleshed out and fully rolled out, what I would expect to see is that we will roll out basically two different sections for washing in the 691. There will be the legacy system, which is just the current ESI with the fixed dates, and then there will be the new system, which will be the predictive Cvm Plus Algorithm. I would expect to see new acquisitions, so new aircraft adopt the new system as part of this push towards digital engineering, and I would expect legacy systems to choose to either adopt the new system or to continue to use the old system. We would probably try to nudge them in the direction of the new system. So both sections would probably get left in the 691, and the legacy aircraft, the aircraft that are currently flying, would either choose the new system or just remain on the old system until they retire.
Okay. Thank you very much, Captain Andrews, for the presentation and answering the questions. Next, I'll introduce our second speaker, Dr. Christine Sanders, who is the lead atmospheric chemist for the Naval Research Laboratory Center for Corrosion Science and Engineering. During her 10 years at NRL, she has worked to characterize the operational conditions affecting DoD assets and the impact that the environment has on the lifetime of the materials. Dr. Sanders received her doctoral degree in physical chemistry from The Ohio State University. Christine, please proceed.
Hello, thank you for that introduction. As Jennifer said, my name is Christine Sanders, and I'm from the Naval Research Laboratory's Corrosion branch. Today, I'm going to discuss a collaborative effort I'm leading between the Navy, the Air Force, industry, and academia. This program that we're working on is aimed to develop a Bayesian model approach to predict the failure of aircraft coatings. During this talk, I hope to share with you a little background about why coating failure is a complex system, examples of how we're integrating a Bayesian model with a physics-based modeling approach to better understand and predict coating lifetime and performance, how we're leveraging large historical data sets to build the framework of our model, the way in which we're validating our model against new rigorous data sets, and finally leave you with a possible end benefit that this scientific understanding could bring to the DoD. So why do we need to predict coating failure? Why is this important for the DoD? Well, corrosion and coating degradation cost the DoD billions of dollars, as Captain Andrews just discussed, through maintenance labor and materials, which includes hazardous waste generation, also system downtime and schedule impacts. In addition, the environmental impact from hazardous materials is something that the DoD is actively trying to reduce. The key point here, as Captain Andrews was saying, is that all of this directly impacts mission capability for the DoD, and that's really the #1 priority. Now you might say, hey, we've been painting things for a long time. Shouldn't we already understand these processes? And yes, that's partially true. However, coding systems are constantly being upgraded and modified. Plus, they're very complex systems to model when you take into account the entire coding stack-up. It's not just like a normal paint that you might use in your home. These coatings normally consist of several layers, which are all interact to protect the expensive assets on which they're applied. In addition, operational environments and conditions are highly complex and always changing. This is especially the case when you consider the impacts of climate change. Finally, although a lot of data exists from previous work, it's a massive undertaking to try to fit all of that into a specific mold to get out something that may be possibly useful. Often these data sets that we've looked at record different environmental data or sometimes no environmental data. And all of this adds up to a complicated database, which is nearly impossible to query. So if we take a step back for a minute, I'm sure that there's probably some people in here who don't spend as much time watching paint dry as we do. So let's talk a little bit about what coatings are. There's primarily three ways by which a coating protects a substrate or base material. First, it can act as a physical barrier by preventing water and corrosive ions from reaching the surface. Second, it can have chemical protection, which we often call an inhibitor. These inhibitors are contained within the coating and are released to protect against ion ingress. Lastly, it can contain a galvanic or sacrificial coating. These coatings have metallic components which will preferentially corrode instead of the substrate. A coating system or stack-up can contain all or some of these. And conversely, there's also three primary ways by which a coating can fail. Something can physically breach the coating, like somebody drops a wrench on it, or a joint flexes enough time that the coating is cracked or broken, and then ions and water can get to the substrate. Second, the inhibitor can be depleted and no longer work to protect the substrate. And lastly, you can also get ions and water underneath the coating, which can start to delaminate or lift the coating off of the substrate. If this happens, then things like galvanic protection can actually work against you. For instance, if you have a noble fastener, then the substrate will corrode to protect the fastener, which is not usually something you want. All right, so I'm telling you that all of this is very complicated. So how do we actually predict anything from this? Well, I mentioned earlier that our team is a large collaborative effort. And so as with all large collaborative efforts, we had a lot of opinions when we first began this project. However, we were able to reach a consensus pretty quickly when we defined a three-light framework. And under this framework, we simplified everything down to three conditions for coating performance. Green, where everything is good, the coating is intact and the substrate is protected. Yellow, the coating is breached, but the inhibitor is still there to protect the substrate. And last, red, this is when the inhibitor is depleted and you start to see signs of corrosion. The coating has failed you. But if you'll recall, I mentioned earlier that predicting coating failure is hard to do. Why is that the case? Well, the outdoor environment has a lot of variables. Some of them are shown here as green bubbles, but we don't have all of the equations to understand how these are related and interconnected. Machine learning can give you a way to look at how they all interconnect through a large amount of data. However, we want to avoid having a model which doesn't build upon already established relationships or may not be adjustable to new inputs. This is where the Bayesian model comes in. It's a cause-consequence model where all of the influences for failure within the network are tied together to predict the probability of failure. Therefore, we can have a combination of factors which we measure, all of that historical data that I talked about, plus factors which we believe are important but are not often measured with high accuracy. In other words, we have to use large amounts of data plus what we know to be true in order to give an accurate prediction. Comparing this to some other machine learning techniques which only predict the best fit and not necessarily the right fit. A Bayesian model really gives us our best guess that we can refine and then collect new and more robust data to work through. In addition, we can also refine some of these relationships by using physics-based modeling. An example shown here is the calculated value that we call inhibitor protection. This is not a known quantity which is easily measured, or at least hasn't been easily measured with older sensors. And historically, the time until the inhibitor is depleted was measured by the first signs of corrosion showing up. That does not give us a lot of data points to make a nice curve. So we can use the physics-based model to help generate the relationship, which will make our Bayesian model more accurate. Here's an example of how the physics-based model gives us a stronger Bayesian model. Inhibitor depletion is a chemical equation. We can predict inhibitor depletion from things like chloride concentration and water layer thickness. This is an example of a process we think we understand the physics behind. So we developed a physics-based model to look at the time to inhibitor depletion and compared it to different locations where there were historical data collected. The experimental data gives discrete data points, but the physics-based model allows a more complete input into the model, including the whole parameter space. And as a bonus, the Bayesian model allows us to input this relationship, even though we don't know all of the equations behind it. In addition to allowing input from the physics-based model, the Bayesian model can also accept data gathered from multiple data sources. As anyone who has poured through someone else's data before will tell you, there's often missing data for whatever reason. The Bayesian model can fill in these gaps with curve fitting and some amount of simplification to give us the data that we actually need for our model. Plus, depending on where the data comes from, some things are measured at different intervals, hourly, daily, monthly, etc. But to add them to a model, you need all of the distributions for these properties over a selected period of time. So in order to build our model framework, we needed a robust way to assimilate all of this old data and show us what data was missing and determine if that missing data is actually important. Even at many of the DoD test sites where we do some of these evaluations, we have limited data, but we ultimately want to be able to predict coding failure for any point on the globe or any period of time in the future. Luckily, the Bayesian model can help to fill in many of these gaps. For example, we have multiple sources of data, even different types of samples, as you can see at the bottom of this slide. When looking back at old data, each previous test we had access to was measuring different things. Realistically, we're not going to use all of these data points. So we want to be smart about how we use the Bayesian model so we're not using extra computation time that we don't need. We need to focus on what's most significant, right? And at the end of the day, we need to be able to validate our model, the most important step in any model's life. And this validation needs to test the adaptability of the model framework. So it's not only giving you the answer you want, but rather the answer that you need. So then what does this model actually look like? Well, here's a small example of a test we can run at a discrete timestamp in a coating's lifetime. We know we can accurately measure things like relative humidity and pH. Time of wetness is sometimes debated, but it's also a measurable quantity. Inhibitor protection is currently a lookup table based on time of wetness, which is actually data regression on an old ESTCP project. This could eventually come from a sensor, but currently we don't have a lot of this data. This is also a case where we can use the physics-based model to flesh out limited past data. The value of the initial charge that's shown here starts with 0% at t = 0, and it accumulates over each timestamp. Whatever the charge value is at the end of the previous month becomes the input initial charge for the next month. And at the end, the model tells us the probability that we're in each of the three conditions stated earlier, green, yellow, or red. This is all then iterated for the next timestamp. After you iterate over enough timestamps, you can get a curve like this to look at the probability of degradation over time. Here we're considering 2 sites in Florida, which we know are very different in both environment and corrosion behavior. Using the actual weather data for each site, we can get a different prediction for how the same sample would degrade over time, with Key West being more stressful for the coating selected in this instance. But then we have to ask, does this actually match the corrosion results from these two sites? If not, then we know we still have some refining to do. We need to go back to the model and see which nodes have the most influence and try to improve the accuracy by having a sensor for that node or a more complete data set. Or again, we can use the physics-based model to add in some of that refinement. When we talk about validating the model, we have a few ways in which we're doing this. The first is through real environment testing at a number of sites. This is a large data set where we're exposing the same samples at different sites at the same time. In addition, there are other samples being exposed starting in different seasons to understand the seasonality of coating degradation. This program used 3 different coating systems which are relevant to the DoD aerospace community that are shown here. However, as Captain Andrews mentioned briefly, sometimes the real world can take a long time to corrode samples. So often in coating evaluation, accelerated chambers are used. Shown here are 2 new methods being developed to improve the accuracy of accelerated testing: the ACES chamber at AFRL and the CRH cabinet at NavAir. As a bonus, our model can help to refine these types of accelerated techniques by pointing to which parameters have the biggest impact on the probability of failure. I should also note here that the CRH cabinet design is part of an ESTCP program. All right, so in summary, through this collaboration effort, we have leveraged data sets from the Air Force and the Navy in order to develop a Bayesian network framework. We have been using physics-based modeling to refine our Bayesian model, and we're currently working on validating the model with high-fidelity testing in both real-world and controlled laboratory environments. With this model, we can input an operational location and coding system to yield information about the most significant environmental drivers and the probable time to failure. From this project, we can imagine a tool where maintainers can easily see corrosion risk based on service environment, and also where designers can understand a probable coating failure timeline from their design. Finally, and importantly, I would like to acknowledge my team and that I can take any questions that you may have.
Great, thank you, Christine. We'll now be open for questions if the audience would like to submit them using the Q&A box. We have received a number of questions. First, Christine, using the model, is it possible to add dynamic factors that might be applicable for a shorter time? For example, flying during wildfires or the effects of more intense short-term exposures.
So that's certainly one of the things that we're thinking about for the future development of this model. Once we have the framework developed where it's robust enough based on larger data sets, then we should be able to present it with some of those more intense environments for shorter periods of time and see what the impact would be. We would, again, want to validate any predictions that the model would give by doing our own side-by-side, testing in the field.
Okay. And have you created training and test data sets from your historical data as a way to test the effectiveness of the model?
So we did a little bit of that, but right now we're mostly just using the historical data for training and then the current data for validation. And we actually have enough sites where we're gathering current corrosion and coating degradation information that we're able to use some of them, a subset for validation, and then if we see that the model needs to be refined, we can use another set for the next round of validation, et cetera. So we have a pretty large data set that we're actively collecting, which is pretty rigorous compared to some of the historical data that we're using.
Okay, great. We have a specific question about joints and fasteners. Are the real-time flex of joint and fasteners used in in developing the model or training it?
So that's a good question. So in order to move to doing sort of like a combined effects test, we have to first start with panels that don't undergo that type of stressor. So this is kind of the first piece. We do have a plan in the next year to do some preliminary work with that type of combined effects testing, but we don't yet have that integrated. So this program still has a bit of time left on it, and we're hoping to add that in at the end.
Okay. And we have time for one last question for you. Coding application quality is crucial to evaluating codings and failures, especially if there's a limited data set. So how is application quality considered in your work, or is that a factor?
That's a loaded question. So I will agree that that is very important. The partners who we have on this program are the labs which do coatings evaluation testing. So we trust that the way they are creating our panels that we're using is robust and is the proper way to do it. Additionally, the data sets, the historical data sets that we were using were from those same laboratories. So it was from the coatings group at NavAir and the coatings group at AFRL. So again, we are trusting them as the experts in coating performance on how they actually applied those coatings.
Sure, makes sense. All right, well, thank you, Christine, very much. And at this time, we'll move to our third speaker. And our final speaker is Dr. Steve Castro, a materials research engineer working with NRL. His research has focused on understanding and modeling degradation in aircraft coating systems and on modeling atmospheric corrosion in aircraft materials. He earned master's and doctoral degrees in materials science from the University of Virginia. Steve, please proceed with your talk.
Hi, can you hear me?
Yes, we can.
Okay, thank you. Yeah, when I took control, I lost the mute button. Good afternoon, everyone. Thanks, Dr. Nyman, for the introduction. My name is Steve Castro, and I'm with the U.S. Naval Research Laboratory. And today I would like to present a snapshot of the work that my colleagues and I have done to model coating system degradation using a combination of equivalent circuit analysis of EIS data, finite element modeling, and physics-based transport modeling to understand changes in a Navy aircraft coating system that was exposed to different environments. Before I forget, I did want to say thanks to my colleagues for their hard work on this project and to SERDP for both sponsoring this work as well as the invitation to present at this webinar. Here's my presentation outline. I'm going to touch briefly on some motivation and why we're doing this work, cover some of the modeling that we're doing, and then at the end hit some of the experimental analysis that we've done that is lending or giving us information to feedback into the model. Now, I will say it's pretty helpful to be presenting as the final speaker of the webinar because both Captain Andrews and Dr. Sanders have already touched on the reasons why we need to model coating system degradation and why it's important to get it right, because of those high maintenance costs and the need to reduce worker exposure to hazardous materials. So I won't go into any more detail here. But it has been alluded why coating system degradation matters from an electrochemical perspective is that below the coating system on an aircraft lies a complex metal structure that's made of different alloys that were often selected because of their mechanical properties rather than their galvanic corrosion compatibility. So hence a coating failure over the joint between a stainless steel fastener and an aluminum alloy skin panel can be quite problematic from a corrosion maintenance perspective because of that galvanic incompatibility between the materials. So here's like a cartoon diagram of the Navy system that we're interested in. It consists of a polyurethane top coat with a given thickness that acts as a barrier coating, as Christine mentioned. Then below that is an epoxy primer that, in our case, has a reservoir of a chromate inhibitor, a barium chromate in particular. And then beneath that is a surface pretreatment that consists of a chromic acid. Part of it was a chromic acid wash that helped to grow that oxide layer to thicken it, and then that helps enhance the adhesion between the epoxy primer and the aluminum oxide. It keeps the coating to stick, allows the coating to stick. And so then we expose that coating system to an environment that includes UV radiation from the sun, water from rain, condensation, or the aircraft washdowns that Captain Andrews mentioned, stresses from flight operations and that these exposures occur over the course of months and years. And so that can lead to age and degradation of the coating system via surface breakdown that leads to electrolyte transport through the coating and leaching of the inhibitor, as well as like crack formation through thickness crack formation that allows water and corrosive ions to penetrate through the coating system right to the substrate. And then again, once the inhibitor is exhausted, corrosion can occur. So our principal data collection was lab-based. We performed EIS measurements of coated panels that were exposed to a variety of laboratory conditions that would simulate environment exposures, a range of environmental exposures. We stressed the coating system, some of the coatings, using a 3D printed static load assembly like you see down here in the lower right. We used various curvatures to apply the stress. Some of our panels had fasteners in them, like this is an aluminum rivet fastener. Others had like a stainless steel threaded fastener, and some didn't have any, but all were coated with the same coating system that was applied per the manufacturer's instructions. And then we sealed the edges or prepped them so that they could withstand. The edges wouldn't contribute to a failure detection, but we made an electrical attachment so we could make the EIS measurements, and then we put the panels into various environmental conditions. So we tested the coating systems in situ, so if they were stressed, we made a custom apparatus that would allow us to put the paint test cell on the panel so that we could make the test without disturbing it. And of course, the flat panels didn't matter. We could just put the paint test cell directly on them and make the measurement. And so we did that over the course of multiple 2,000 plus hours. I guess we're up to 6,000 hours in some of them. So we said we use EIS as our principal method of getting data about the coating system, but on its own, that provides an incomplete picture of the state of the coating because there's multiple contributors to an impedance measurement. Equivalent circuit modeling, though, provides a way to get insight into what each of those contributors is doing because it allows us to assign an underlying mechanism to standard circuit elements. So we get estimates of the equivalent circuit element parameter values by using nonlinear regression to fit the model circuit's impedance to the measured impedance. And if we choose a useful equivalent circuit, we can obtain information about the coating system as well as the underlying substrate from the EIS data. So on the left here, we have the little blue symbols are the measured coating impedance for a panel that was, I think this one was immersed over the course of 2,000 hours. And then we use this coating equivalent circuit to fit the circuit's impedance to the data that's represented by these red lines. And I've highlighted here the different circuit elements. So this resistor and capacitor, those values give us information about the oxide. This capacitor and this resistor give us information about the coating. And this last resistor tells us about the solution resistance. And we're going to focus on this resistor here. We're calling that the pore resistance of the coating system, and how that changes over time is what's going to give us information about the way the coating system is behaving. So we can use a combination of a physics-based approach with simple regression models to fit the change in the pore resistance of the coating system over time in response to our laboratory-based exposure conditions. And we can see there's a difference in how the coating system responds to immersion exposure versus exposure to static stresses in UV light. So this blue line is our model for a given set of conditions for a panel that was immersed in electrolyte with a given chloride concentration. And these red lines are how the coating system pore resistance responded when the panel was stressed and exposed to UV light in a condensation in the QUV chamber. And you can see the behavior is different. The pore resistance declined more slowly in the GUV chamber, but with the stress and UV light, it was at the asymptotically, it declined to a much lower level. And so we think that eventually that one will drop down to actually breaking that like sort of 1 mega ohm per square centimeter resistance that we call as a failed coating system. So those conditions seem to be more aggressive than just simply immersion. So in that previous slide, that's our first physics/regression model for coating degradation. We know that one way to improve that model is to account for the electrolyte on the surface of the coating. And Christine kind of mentioned this in her presentation as well. The water layer that forms on the surface will change in response to environmental changes, such as temperature and relative humidity, and because we know that water layer is going to try to equilibrate with the environment. For example, if that the electrolyte forms from salt crystals that have been deposited on the coating surface, as the temperature and relative humidity pass through the deliquescence point for the salt, water will condense on the surface and form that electrolyte, but it will be in a very nearly saturated concentration. So this little red line is where our electrolytes formed. It's 6+ molar sodium chloride. But if our environmental conditions, in our case, for this model, the relative humidity was 90% and 25 degrees C temperature, that's not stable. So we're going to get additional condensation, and the water layer will grow as more water is added, which will decrease the chloride concentration down to a level where the liquid water is now in equilibrium with the water vapor in the air, and that's going to have us much more water, and that water is now available to diffuse into the coating. Of course, chloride will go with it, but at a first approximation, we're just going to look at the water diffusion through the coating. So the next model now is we're going to look at the transport of the water through the coating system. And our first approximation was to treat the coating as a one-dimensional layer for the water to diffuse through. And we can model that the water concentration profile over time. Here went from 0 to 1,000 seconds. And we get very rapid water uptake under this model. And the coating system property changes occurred much too rapidly from what we observed experimentally. So our next refinement was to take that one-dimensional model and say, okay, let's treat our coating system as a two-dimensional layer, two-dimensional structure, where we have water diffusivities that change depending on what the coating layer is made out of. So our polyurethane top coat will have a water diffusion coefficient that's different than the epoxy primer. We're still solving the same diffusion equation, and we have to have boundary conditions on the sides and on the bottom that we can specify as either static or as insulated boundary conditions. But we know that the water concentration on the top layer has to be whatever the electrolyte, the composition of the water in the electrolyte is. So that's set. And so we could solve the diffusion equation over time. Here, and this is the diffusion coefficient now. It varies as a function of the thickness, of the depth of the coating system. And now we plot water concentration profiles where we're looking at the center of the coating system from the top down to where the metal layer is. And you can see that it varies over time, and the slope changes depending on where you're on the coating system, because water transport is faster. They are slower in the top coat, so you get a much steeper slope versus when the water reaches the primer, where it's faster, and so it can get to the metal surface more quickly. And so this 2D approach improves the accuracy of the model, but it's we need to refine how we're calculating the coating resistance based on what the water uptake in the coating is, so we can match it with what we've fit from our equivalent circuit models and how we detected it changed over time. So that's still an active area of development. And so another area we need to incorporate into the model is this calculation of stress fields in the coating system that arise from the underlying aluminum structure in the fasteners. And so we're focused around the holes where the fasteners are placed into the skin panels of the aircraft, because that's where the stresses are highest. So when we apply the coating system, that's now basically mechanically fastened to the aircraft surface. And so when that surface moves, those deformations get communicated to the coating system and introduce strains and then stress fields in the coating. So so as you could see here, that the stresses vary there's a lot of variation in and near these countersunk holes, and once you get away from them, the stress fields equilibrate out. So that's why we're focusing on the fasteners. So that's where we think the greatest chance of a coating failure would be. And we also modeled two cases, a carrier landing case and a high G maneuver load, because in both cases the fastener is going to move differently than the coating surface, and so that's going to introduce deformation into the coating system with resulting high stresses. And so we've started being able to capture some crack formation in the coating system, but we haven't. Look, we need to link that now into trying to capture that as an electrolyte transport pathway from the surface to the metal. That's still an area that we're actively working on. And so we've performed some post-mortem analysis of the coating systems that went through different exposures. I think these were ones that completed like 2,000 hours of exposure. And so you could see here in the micrograph on the left that we can identify the top coat, the primer, the oxide layer, and then the aluminum substrate, and very clearly from the composition using EDS to detect the silicon and titanium dioxide. That is the top coat, and in the primer we have the chromate filler, so you can clearly see the chrome peaks in there, so we can differentiate between the two, and then the aluminum oxide. And we focused on looking at the stressed panels, because even though those are static stresses and not fatigue, so that was then with the UV light we saw, and with the pore resistance changes, that those were the more aggressive conditions. And so while we couldn't actually image a mechanical failure in the coating, a crack through the coating system, because those are hard to see, we were able to detect chloride that had basically diffused through the different layers of the coating system. And at the junction between the coating and the aluminum substrate where the oxide was, we did see in the stress panels where cracks had formed in the oxide layer. And then below the oxide, we saw in some cases subsurface corrosion. And so we also detected chromate peaks inside that corroded region. So we think what's happened is that water penetrated through first, chloride followed as the availability of chromate that had leached out and into the water layers eventually deposited out, so chloride could follow. When the chloride got through the cracked oxide layer, corrosion occurred that created a void, and then we got additional chromate leaching into that volume out of the coating. So I don't think that this pit is continuing to propagate, but of course, once the chloride in the immediate vicinity that can reach that area deposits on the surface, the pit could reactivate if we get more corrosive electrolyte in there and continue to grow from that. So this all proceeded without actually, as far as we can tell, a crack or a through thickness crack in the coating system, which is interesting because that means the electrolyte is able to get through and cause corrosion independent of like a visible mechanical damage. So just to wrap up here, I'll touch on a couple highlights. In terms of the modeling, we have so far a two-part phenomenological model of the coating system degradation that includes tracking the parameters that we obtained from our EIS measurements to determine the state of the coating system, and then using diffusion models to try to estimate electrolyte transport and relate that back to the pore resistance that we're still working on to incorporate stress fields and the other like UV light as an environmental degradation parameter. And we've identified that like electrolyte transport occurs independently of mechanical failure of the coating system. So that's another path for that could be a failure could be occurring underneath the coating that isn't visible. But UV and stress do exacerbate that degradation. And then in terms of benefits to DoD, we're trying to develop a software package that we would, an open source software package using a cross-platform approach that we hope to be able to transition into a tool that could be used by maintainers that would be able to provide options to select models depending on the needed predictive capabilities. And I have on the right here two of the software pieces that we're working on, and the UX is probably terrible, but I mean, we're scientists, not necessarily computer scientists, but the idea is like, okay, we have a physics-based model that does incorporate some regression models to fit to our EAS data, but that provides one suite of modeling capabilities to a maintainer. But as you saw, like Dr. Sanders' work, they're using a Bayesian model. But it would be nice to have eventually arrive at a software tool that would allow the maintainer to decide which one is the one they need for their particular application, or to obtain the information that they need that they can select and run in a software that the Navy or the Air Force could have developed for them. So that's where our hope is to eventually take this program. I have no idea how much time it took, but with that, I'll wrap up and ask for any questions. Thank you for your attention.
Wonderful. Thank you, Steve. If any members of the audience would like to submit a question for Steve, do that now using the Q&A box. We do have a couple questions for you. First, Steve, would you explain your choice of equivalent circuit for your EIS modeling? Specifically, why is the coding C in parallel, but the coding R is in series with that of the oxide layer?
Yes, that is a very good question. It's because the coding circuit that's came out of some older papers that looked at developed this, but I think it's because there's between the electrolyte layer and the substrate, the coating system itself acts as a capacitor, like a charge separating layer. So that's why the capacitor is in parallel with the oxide, but in series with the resistor, because the charge can build up, like charge separation can occur from at the electrolyte coating interface, and that the coating then acts as a dielectric, and so that's why the capacitor is in parallel. But if you actually were to have the charge migrate through the coating system, it would have to pass through a resistor, then reach the oxide, where it would see another like dielectric in terms of the oxide to a metal interface. And if it had to go through that, it would have to pass through a resistor, or it could get stuck there as a charge separator. Hopefully that makes sense. I'm gesturing with my hands that you can't see, but I'm trying to illustrate that. And hopefully that makes sense.
Perfect, thank you. And Steve, how do you relate the laboratory exposure data to the atmospheric site data?
Well, yeah, that's going to be a big challenge. Our hope was that when we planned out the experimental the conditions, was to sort of encompass the range of the atmospheric exposure site conditions that an aircraft would see, like at least the Navy aircraft would see, so that we would capture, so even though we weren't exactly replicating a particular site, that we would capture the range of temperatures and a range of relative humidities and the chloride concentrations that it would see. We would get to the extreme ends, either very low or very high on all of those parameters, so that it would be encompassed in that large parameter space, and we hopefully wouldn't leave anything out. So the idea is to be able to relate it that way.
Okay, thank you. Are the results of this analysis fed back at all to the suppliers of parts or the aircraft to drive some changes in new purchases or upgrades?
Wait, I'm sorry, was that directed to me? I missed the very part.
Yep. Yeah. So, so do the results go? Do you know if your results ever are provided to the suppliers of the parts or the aircraft to drive some changes in new purchases?
Well, Robin probably hopes that we do that one of these days soon. Yes, we did not. It's not so far yet, but hopefully through the results here and as these projects reach completion, the transition would be to provide this information back to the fleet, in our case to the Navy, but for the Air Force, back to them as well.
Okay, great. Does the EIS modeling show decreased resistance with time? And then does that suggest electrolyte penetration?
Yes, sorry. So that over time, that pore resistance is decreasing the longer it's exposed to these environmental conditions. That's why we're using that as a proxy for the coating degradation. At some point, the inhibitor is leaching out, and we're not seeing that in the EIS data. That may be occurring at a level below what we can resolve, but we're using the pore resistance decrease as a proxy for the coating system degrading.
Okay, Got it. Thank you. So at this time, we would like to bring back Christine and Captain Andrews, and we have a couple of questions about how the projects might link to each other. So Steve, the first question is for you. What is the relationship between the physics-based models and machine learning models for coding degradation? So for example, could your physics-based model be integrated with Christine's model?
Well, right, that would be I guess the goal here would be to use where there's gaps, because so for a machine learning model, in order for it to be effective, you have to have example cases that cover the entire parameter space of what things can happen, because the machine learning model can't, I guess, depending on the type of model, it's difficult to always trust if it has to extrapolate outside of the parameter space where it's been trained. But the physics-based model, if you've captured the right physics, could do that. So this would be a good place. So if there isn't available data for the machine learning model, that if the physics-based could provide a way to to bridge a gap in data, that would be a good way for that to help while you're waiting for the machine learning to catch up. Because you need like hundreds and hundreds of data points usually to train, or even thousands to train a good machine learning model. So if you don't have that, but you have a reasonable physics-based model, that can help provide you a stopgap.
Okay, great. Next, Christine, can your model be used with current data from WASH studies, like the study that Captain Andrews presented?
Yeah, absolutely. And we actually have some other projects that Captain Andrews has been helping to advise on, looking at WASH studies. Those are other things that are going on at NRL in Key West. And I think that's ultimately the goal of this big Bayesian model type system is, like Steve said, we have physics-based models to define the parameter space, and then we can insert real world data where we have it. And through that process, we can build a really rigorous model which could predict different types of factors, like how does washing affect it, because you're looking at the changing time of wetness and removing chloride layers and all of those components which were kind of laid out in our nodes. And maybe there's even some parameters that we initially didn't have in our framework. And by looking at the physics-based modeling and more extensive data sets, we can start to add in more nodes to fill in those gaps.
Okay, great. And then finally, Captain Andrews, there is a lot of interest in your study, and there was a question about when a report or article might be published on this study.
So we're currently in the process of our data collection. We had to extend it for longer than the project was initially scoped for. This project was conceived in 2016, I believe. So we're on 5 years right now, and we've had to extend data collection because we weren't seeing nearly as much corrosion, and especially any differentiation between the wash cycles for how long they've been out there so far. So still collecting data. The algorithm itself, like I said, is in its sort of first stages. There's an initial draft of it, but it hasn't really been trained yet. But there's some really neat data going on behind the scenes with that really hope we can share, in about 6 months with the wider community. So I would expect to see a report just on the exposure algorithm probably sometime in the spring, and then there's still a lot of work to do on actually rolling out washes. I sort of, depending on where the ESTCP committee wants to go and how far they want to go, I imagine a report could be made available for them, summer or fall of next year. But we still, in order to actually get this into the TO, would need to do a field service evaluation, probably with a couple of platforms in various places, just make sure, like I said, the real world correlation actually makes sense. And that could take a couple of years. So in terms of a project report, it could be made available sometime next year, but in terms of actually getting this rolled out to the TO for fleet-wide use, you're looking still at 3 to 5 years, I would imagine, just to complete those field service evaluations.
Okay, thank you, understood. As we wrap up the webinar, I'd like to check in with each of our speakers for just one last message to leave with the audience. So you would each think of just one conclusion from your work that you would like to highlight or emphasize with the audience. Then please provide that. And we'll start with Christine and then Steve and wrap up with Captain Andrews. So Christine, one last conclusion.
You're putting me on the spot here a little bit, but that's all right. But I think, through my graduate work, I did some modeling and I also did a lot of experimental work. And I think that what we've really seen, and I think the larger community always agrees upon, but maybe doesn't always follow through with, is that you always have to have a model and experimental data working in concert. And I think that's where you can really come through some of the challenges that exist with different types of computer learning techniques. You really have to have that validation of real world data, or else the model just isn't going to be trusted and won't transition to a usable product.
Perfect, well done on the spot. Great message. And Steve, one last message.
Well, I was just going to say that it was really great actually seeing like the work from Captain Andrews and what they're doing over in the Air Force, and that I guess that's why these are really important to have like these type of webinars so that we get the exposure, because I tend to at least focus on just what I'm doing, and so it is nice to see what other folks are and to see potentially for where connections could be made to improve or or to other application for what I'm doing, or how I could maybe help, or where his data could be incorporated into what I'm doing. I thought was a nice takeaway. Very interesting. Both talks, both Christine's. I'm a lot more familiar with Christine's, but I hadn't seen Captain Andrews before, so that was interesting.
Thank you, Steve. And finally, Captain Andrews.
Yeah, I'd kind of just like to, say how encouraging it is seeing, some of these projects I'll get briefed at the same time, and especially with how Dr. Sanders' work is and I know a number of her projects now are working very closely with AFRL. In the past, the services have tended to stovepipe their own projects and ideas, and they end up going in wild directions and doing their own things. But I think we're really starting to see, a convergence again, of especially between the Air Force and the Navy, and we're bringing Army and Coast Guard aviation in as well. Actually starting to work together, and hopefully going to see the development of some heavy-hitting actually DoD aviation standards and practices over the next few years. It's going to be, I don't know if exciting is the right word, but an exciting time in military corrosion maintenance over the next handful of years.
Wonderful. Thank you to all of our speakers today. And as we wrap up, our next webinar in this series is on Thursday, November 18th. That will discuss open source tools to unlock data and optimize building operations. Registration is open for this and other webinars, so please visit the webinar webpage for SERDP and ESTCP to register. And I would like to remind you that both the audio and a copy of the presentation of today's webinar will be archived on the webinar webpage in case you want to refer to them in the future. And we would appreciate it if you could please take a moment and complete the survey that will pop up on your screen at this time. This concludes today's webcast. Thank you.